Hey guys, today we're going to talk about behaviors of implicit relations. For this entire unit, we've been talking about functions exclusively, but we're going to look at how things like the first derivative test applies to relations that aren't necessarily functions. So here you have an example of a relation that's not a function. You can see that right away because it doesn't pass the vertical line test. If we throw some vertical lines on there, that's a no-go. So there's a relation there. X and Y obviously have a relationship, but it's not a function. So why is this curve considered an implicit relation? We use implicit differentiation when X or Y can't easily be solved for. In other words, they're so connected, it's hard to get one or the other by itself. So it's hard to solve for Y, especially because this is not a function. All right. So at what points does the curve have vertical tangent lines and where does it have horizontal tangent lines? So remember, we're looking for places with a vertical slope or an undefined slope. That happens here and here. If we were to sketch some tangent lines, those are clearly undefined. And then where does it have horizontal tangent lines? It doesn't. There's nowhere on this graph where there's anything horizontal. So no horizontal tangent lines. So horizontal tangent lines, none. But vertical tangent lines, we do have some. We have one at the point -2, 0, and one at the point +2, 0. All right, in which quadrants is the curve increasing and in which quadrants is the curve decreasing? If we look at our quadrants, remember this is 1, 2, 3, and 4. When you're looking for increasing or decreasing, you're looking for positive or negative slopes. Don't forget to think about your old friend Slope Dude. So for example, if we focus in right here on quadrant 1, if we put Slope Dude here and he skis from left to right, is he about to say puff, puff positive or nice negative? So since he's going uphill from left to right, the curve is increasing in quadrants 1 and 3, and then the curve is decreasing in quadrants 2 and 4. All right. So we've looked at this graphically. We've seen where the slopes are increasing and decreasing. We've seen where there's vertical tangent lines. But now we're actually going to get to the heart of the algebra. So algebraically, let's find the derivative. We're going to find dy dx, and we're going to use implicit differentiation to get that done. So it might be a little while since you've done implicit differentiation. So just as a quick review, remember, our function is x squared over 4. I'm going to write that with the 1/4 factored out just because all of our brains seem to like that a little bit more, mine included. And then just as a reminder, y is not a variable. Y is a function. It's been a while since we've written it this way, but it's y of x. We take the derivative of the inner, the derivative is going to be dy dx, and then we take the derivative of the outer, so whatever's being done to it, in this case, I'm trying to erase, in this case we have a y squared, so we're going to take the derivative of the outer. So remember that y is a function, y of x equals 1. So let's take the derivative. We're going to get our power rule on over here, bring down that 2. 2 over 4 is 1/2 x minus outer, we're going to bring down that 2y, and then inner, the derivative of y is dy dx equals 0. Now our goal is to find dy dx, so we are now going to work on getting dy dx by itself. So we're going to start by taking this 1/2 x and subtracting it from both sides. And if it's okay, I'd like to put that back into fraction form. So -2y dy dx equals -x over 2. The reason is we are about to divide both sides by this -2y. And if we already have a fraction, it's easier to put it in the denominator. So we're going to have dy dx. We're still going to have that -x in the numerator, but now joining us in our denominator, we already have a 2, so 2 times -2 is -4y. And then, of course, those divide away, and I'm going to be lazy and just divide my negatives away. So dy dx is equal to x over 4y. I divided too much. Okay, so we found dy dx. Remember that this is an equation of slopes. In order to find the slopes, we have to put in an x value and a y value. And that's important because x values don't cut it. If I asked if the slope at 6 is positive or negative, you'd tell me, I don't know, there's 2 slopes at 6. So implicit differentiation is important because you not only put in an x value of 6, you also put in a y value, like you're looking at the 0.63 or 6, -3. So just a reminder why this is important. All right, so looking at dy dx, when is it undefined? When does it equal 0? So remember, dy dx is represented here by a fraction, x over 4y. So we want to ask ourselves, when are fractions undefined? Fractions are undefined when we try and divide by 0. So when the denominator is equal to 0, that's when a function is undefined. So what value would cause this denominator to equal 0? In this case, y equals 0 would cause us to divide by 0. Remember, dy dx is slope, so when y equals 0, that tells us that dy dx is undefined. Or not equals, but is undefined. And that's another way of saying we're going to have an undefined slope or a vertical tangent line. So we'll look at that in the graph in just a second. Let's go back to how do we know when dy dx equals 0? Well, when we're looking at a fraction, if the numerator equals 0, we know that the whole thing is going to equal 0. So when does that happen? In this case, x equals 0. Remember, in that case, that tells us that dy dx is equal to 0, and that's a horizontal slope. So we know we're going to get vertical tangent lines when y equals 0 and horizontal tangent lines when x equals 0. How does this support our answer to question 2? Well, question 2 asked us to find where are there vertical tangent lines, where are there horizontal tangent lines. So let's start with the vertical tangent lines. Those occur when y equals 0 because those are the places the slope is undefined. So let's go up to our graph. Where does y equal 0? Right here and right here. Well, wait a second. We already figured that out graphically. We know if we made a tangent line there, that would be vertical and that would be vertical. So we already found that right here. What we just did is we proved it algebraically. We know it graphically because the slopes are vertical, but now we know it algebraically because if we look at our derivative right here, we know it's undefined, literally undefined, when y values equal 0. So let's take a look at when we're going to have 0 slopes. That occurs when the input is equal to 0. The x value is equal to 0. If we go up to our graph, where is there an input at 0? Well, there's not one. If we look at 0, there's no input anywhere. So that means there's no output with a slope of 0. And that makes sense because nothing even exists there. So remember when we got none? Sorry, my calendar. Please go away. There we go. We got none for horizontal tangent lines. And that makes sense because the places where the derivative would have a output of 0, the graph doesn't even exist. It's not defined there. So let's use dy dx to justify our answer to question 3. Remember, dy dx tells us where the curve is increasing and where the curve is decreasing. So remember, our slope equation is dy dx equals x over 4y. When is it going to be positive? It's positive when x and y are the same sign. A positive over a positive or a negative over a negative. And where does that happen? That happens in quadrant 1, where the x's and y's are both positive, and in quadrant 3, where the x's and y's are both negative. The same thing is true, and dy dx is negative when x and y are opposite, have opposite signs. And when do x and y have opposite signs? That happens in quadrant 2. Oops, that's not a 2, that's a 3. And quadrant 4. So when you're dealing with fractions, if the signs are the same, positive. If the signs are opposite, negative. All right. In which quadrants are the curves concave down, and in which quadrants are the curves concave up? You can look at that graphically. Remember, down like a frown, up like a cup, so we can see when the quadrants are down and up. But we can also think algebraically. Actually, let's just look at this graphically for now. Concave down. That happens in quadrants 1 and 2. And concave up, that happens in quadrants 3 and 4. Okay, the reason I wanted to just talk about it graphically, again, if we go up here and look at the graph, you can see down like a frown, up like a cup, up like a cup, is because on the next page, the second derivative is given to you. So we found it graphically, let's support it algebraically. Remember, the second derivative gives us concavity. If the second derivative is positive, concave up. If the second derivative is negative, concave down. So notice here, we have a fraction, and we want to know the places that this is positive and the places that this is negative. So notice in our numerator is already negative. So we know that this overall fraction is going to be positive when the signs are the same. So let's look at our denominator. For our overall second derivative to be positive, we need a negative over a negative. So let's write it like this. The second derivative is positive I'm just going to erase this to give me some room. When y is negative. And when does that happen? Because the whole thing's positive because we're going to have a negative over a negative. That happens in the Did I write this right? Yes. Okay, sorry. I got nervous. I wrote the wrong answer to number 7. I did not. Okay, so that happens in the third and fourth quadrants. And that's exactly what we said in question 7. So the second derivative is positive when y is negative, and negative. And remember, positive tells us concave up, and negative tells us concave down, just as a reminder. When y is positive. And when is y positive? In the first and second quadrants. So does this curve have any relative extrema? Why or why not? Well, remember, the potential for relative extrema can only happen at critical values. And remember, the critical values are defined when f prime, or in this case, we're saying dy dx because we're doing implicit differentiation, when dy dx is equal to 0 or undefined. We already found those locations, remember? It doesn't equal 0 anywhere, and it was undefined at -2, 0, and +2, 0. And are those relative extrema? Well, let's go look. Those two locations are critical values, but are they relative extrema? Let's see if I can make it over there. Okay, I can't make it over there. Hang on. Okay, got it. Let's check those points. Is this a max or a min? Nope. Is this a max or a min? Nope. So remember, just like with any other function, we check the critical values. And in this case, does it have any relative extrema? Why or why not? Because the only critical points are negative 2, 0 and positive 2, 0, and those are not extrema. The critical values are not extrema. All right, so we played around with that function a little bit so we could talk about different things like its first and second derivative and look at the different quadrants. Now let's formalize a little bit. So implicit differentiation can be used to find the first and second derivatives of relations, not just functions. Whoa. I don't know what's going on. I'm sorry. All right, I quit and came back, so hopefully it'll work now. So we're going to be looking at any kind of relations, not just functions. Remember, critical points are now the x and y values. Now they're the coordinates. They're not just the x values. So think x and y, where dy dx is equal to 0 or undefined. So that's not a new definition of critical values. The only thing that's new is now we're looking at specific x and y locations. So make sure that those points are on the original relation. Earlier, we tried to find horizontal slopes when x equaled 0. That wasn't on the relation, so make sure they're on the original relation. So remember, a curve is increasing when dy dx, the first derivative, is positive, and decreasing when dy dx is negative. So y'all, this is still true. The only real difference that we're doing here is instead of just looking at x values, we're looking at coordinates, x and y's. That's the only thing that's really new here. A curve is concave up when the second derivative is positive, and concave down when the second derivative is negative. Again, we've already solidified this. And then the second derivative test can also be used to identify extrema. Okay, here we go. Let's get down to brass tacks and just do some examples. So consider the function g of x equals y, whose curve is given by the equation 4y squared minus 14 equals y times the cosine of x for when y is greater than 0. All right. We want to show that dy dx is this output by doing this ourselves. So here we go. Let's start by writing down the original function. 4y squared minus 14 equals y times the cosine of x. All right, let's start with the left side. So remember that we're deriving with respect to x. We know that. So if we run into any other variable that's not an x, we don't treat it like a variable. We treat it as a function of x. So let's start with the left side. We're going to bring down that 2. So 8y dy dx. And then the derivative of 14, just good old 0. Equals, and then we're going to use the product rule here and everything's going to be okay. We're going to do second times d first plus first times d second, and we're going to be just fine. All right, here we go. Second times d first plus first times d second. And everything is okay, and we're doing just fine. So now, remember, we want to show that dy dx equals this whole mess over here. Remember, our goal is to get dy dx by itself. So right now, we have a dy dx on the left and a dy dx on the right. So let's get this bad boy over to its bestie. Let's get those dy dx's together. So 8y dy dx minus cosine of x dy dx equals, and if it's okay with you, I'm going to do a little bit of multiplying here, negative y sine of x. Now what we can do is we can factor out a GCF. Both of these have a dy dx in them, so we can factor that out. So let's factor out dy dx, and we're going to be left with 8y minus the cosine of x equals negative y sine of x. So we're almost there. We want to get dy dx by itself. It's being multiplied by all this other garbage. So how do we undo multiplying? With division. So dy dx is equal to negative y times the sine of x over 8y minus cosine of x. So we're super duper close to being done. The only thing that's wrong is if we look at the signs, they don't match the original, but that's okay. If we multiply everything through by a negative, and that's okay to do, because if we do -1 over -1, we're really multiplying by just a 1, so it's okay to multiply the top and the bottom through by a negative. It's allowed, I promise. We'll have dy dx equals y sine of x. And just to make it match the other one truly, I'm going to put that positive cosine x in the front and a negative 8y in the back. And now we have shown it. Our goal was to show it, and we showed it. So that was just a little practice in implicit differentiation. So now we want to know, is g increasing or decreasing at this point? Well, we know that a slope is, or a function rather, we know that g is increasing when the slope is positive. And we know that g is decreasing when the slope is negative. So if we want to find if g is increasing or decreasing, let's see what its derivative is doing. Let's see what dy dx is doing. So we want to find dy dx specifically at the point pi over 2, root 14 over 2. So what we're going to do is we're going to take those values and substitute them in, and we don't even really care what the output is as long as we figure out if it's positive or negative. So let's do our y value, root 14 over 2 times the sine of pi over 2. And the sine of pi over 2, if you think about your unit circle, that's just 1. And then down here, we're going to have cosine of the pi over 2 minus 8 times our y value, which is root 14 over 2. So now we can simplify this slightly if you're not sure how it's all going to turn out. We know that sine of pi over 2 is just 1. So our numerator is going to be root 14 over 2. And then we know cosine of pi over 2 is 0. So that's going to be 0 minus 8 times root 14 over 2. And y'all, this is enough to show that we have a positive over a negative, which means our derivative is less than 0. A derivative being less than 0 means your slope is less than 0. And if your slope is negative, it means that g is decreasing at pi over 2, root 14 over 2, because the derivative dy dx is negative. And you might be saying, huh, how does g relate to dy dx? But we know that g is the same thing as y. So dy dx, the derivative of y, is the same thing as g prime. So if you wanted to say g prime is less than 0, that is mathematically equivalent. Either one's okay. All right, next one. For 0 to 2 pi, find the coordinates of the point where the line tangent to the curve is horizontal. So reminder, here we have our derivative. We know that tangent lines are horizontal. That's another way of saying a slope is 0. So what we really want to know is, when is this slope equal to 0? We know that this whole thing is going to be 0 when our numerator is equal to 0. So the entirety of dy dx is going to equal 0 when specifically y times the sine of x equals 0. So let's find when that's true. When is y ever going to be equal to 0? Well, it's not. Here, let me use a different color. We know it's defined up here that y is bigger than 0. So can this term ever equal 0? No, y never equals 0. So now let's find when sine of x equals 0. When does sine of x equal 0, specifically on the intervals from 0 to 2 pi? That happens when x is equal to 0 and x is equal to pi. So we know the x values, but this says find the coordinates. So we want to find specifically the xy coordinates. So we know it's going to be 0 something, and we know it's going to be pi something. So let's find those somethings. How do we know the outputs? We plug them into the originals. So let's start with x equals 0. X equals 0, substituted into the original function. We need to find our y value. So our original function is 4y squared minus 14 equals y times the cosine of x. And in this case, because x equals 0, we're going to substitute in 0 into our cosine. So because x equals 0, forgive me, this thing is freaking out again. Because x equals 0, then we're going to substitute 0 in for our x right here. All right, let's see if this lets me write. Okay, apparently my pen died. Hang on. Okay, we're going to put a 0 right here, cosine of 0. And now let's solve for y. So in order to solve for y, we're just going to keep cleaning this up as much as we can. So 4y squared minus 14 equals y times the cosine of 0, which is y times 1. Now we're going to get all our y's on the same side. So 4y squared minus y minus 14 equals 0. And then we're going to get our factor on. So 4y plus 7 times y minus 2 equals 0. So our possible solutions are y is equal to negative 7/4 and y is equal to 2. But remember that y is positive. That's super important. So this is an extraneous solution because this is the only possibility. So one of our coordinates is when we put 0 into the original, we get 2 out for our y value. So now we have to do the same thing with pi. We're going to put pi into the original and see what we get out for our y value. So when x equals pi, let's substitute that into the original. 4y squared minus 14 equals y times the cosine of pi. And the cosine of pi is negative 1. So 4y squared minus 14 equals negative y. Get all those y's on the same side. We're going to have 4y squared plus y minus 14 equals 0. Then we're going to factor 4y minus 7, y plus 2 equals 0. And then our possible answers are y equals 7/4 and y equals negative 2. But again, y has got to be bigger than 0 because that was defined for us. So the only possibility here is 7/4. So we're going to come over here and say 7/4. So these are the coordinates that make this a true story. Those coordinates make dy dx equals 0, and therefore they are the points where the curve is horizontal, because remember, when it's horizontal, the slope is 0. All right, last one, multiple choice question. A function passes through the point 1, 3 and has a derivative given by 3x squared minus y. Which of the following statements is guaranteed? So let's see what happens when we substitute 1, 3 into this function. So our x is 1, our y is 3, and we're going to put those into the function. So dy dx is specifically at the point 1, 3. You can use this notation if you want to. Is equal to 3 times 1 squared minus 3. And 3 minus 3 is 0. So if the slope is 0, it means we've got a critical value, right? It's a max or a min. Hooray! So let's see what we can do here. You can either make a vertical line, but wait, Things are tricky here. How do we pick points to the left or to the right when we also have a y value? There's that element of we can't just pick left or right when there's also up and down involved. We don't even know what the original function looks like. So instead, what we're going to do is we're going to use the second derivative test. First derivative test ain't going to cut it. So let's find the second derivative. And that's going to be 6x minus dy dx. And this is a little crazy, but since we already know what dy dx is, it was defined for us up here, we can write this as d squared y, or sorry, I wrote that wrong. D squared y, dx squared, d squared y, dx squared. And that's going to be 6x minus 3x squared minus y. And let's evaluate that specifically at 1, 3. So d squared y, dx squared specifically at 1, 3 is going to be equal to 6 times 1 minus 3x squared is 3 minus 3, which is just 6. Now remember, second derivative tells us it's concave up. So we know we have a critical value here, and we know in our second derivative, it's positive. 6 is greater than 0. So if it's concave up, what are we looking at? We're looking at a relative minimum. Okay, you did it.